Hi and welcome to the podcast. Today on the first episode, I have the one and only, the PCB expert, the optics PhD, Midwestern Engineering CEO, Zach Peterson. Welcome.
Thank you so much. Yeah, I know all about getting started podcasting, so I'm always happy to help someone out with their dive into doing this. So that should be fun.
Okay, thank you. Appreciate it. So today I have asked you to prepare something for today, and I think it's a super underutilized topic in DIY audio, and that would be PCB design for audio DACs. If you would be so nice to tell us about yourself a little bit.
Yeah, definitely. So most people probably know me from the Altium Academy YouTube channel. And then if you've ever read any articles on PCB design, there is a high chance that either I'm listed as the author or I ghostwrote it for another company. So I've been doing this for, it's coming up on 6 years now. It's crazy how time flies. But I wouldn't do anything else. So I hope I can do PCB design the rest of my career. So just a bit about my background. So I didn't get started in electronics as specifically to do electronics. So when I went to college, I studied physics, and I had this idea in my head that I was going to be, Professor Zach. And I did that for a little bit. I was an adjunct, and I preferred to retire into being a professor rather than doing that for my whole career. But eventually shifted into optics and lasers, and my PhD research was in a topic called random lasers. And it's this kind of niche topic in nanotechnology. And I kind of had to do everything. I had to do, the fundamental theory. I had to build the actual experiments. I had to take the data, to analyze it. I had to make the devices. So, we were already a small group at Portland State University, but then me doing everything on that project, because I was the only person, really gives you a lot of experience. And then kind of as side topics, we also did metal oxide semiconductor devices, so electro-optic devices, back-to-back diodes, solar cells, things like this. So that was a lot of fun, learned a lot, and then eventually kind of drifted around after university for a couple of years, trying to get a job, because making a transition from academia to industry can be very difficult. And eventually just kind of threw my hands and started doing odd jobs and freelancing. And then people in the electronics industry found me, asking me to do things like research and design and analysis of design. And then I learned PCB design. And once I started to work directly with Altium, I didn't look back. I said, I'm going all in on PCB design because this is working. And kind of the scope of what I did with them and what we do has grown over time to now handling their podcast and running the YouTube channel. And it's very rewarding, and I enjoy doing it. And we get such a great response from people in the community who want to learn about PCB design, really in all areas, whether they want to do, wireless, or whether they're trying to do, embedded systems, so like high-speed digital, or if they want to do audio, low-frequency analog, low-level analog, which is, specialty or, test and measurement. So those can be very difficult topics. So yeah, I've done a lot of different designs, and kind of had to be one of Altium's experts on all of these different areas of design. And it's a lot of fun. So that's how I get to where I'm at today, speaking with you.
Look at you, a scholar, engineer, and a celebrity in one package.
Well, I guess so. I let other people say that stuff, and I'm not going to say it about myself. It's only true if other people say it. It's like the peer review system, right?
Yeah, it's true. It's true, but that's how I found you, via the Altium channel. I was looking at your videos, trying to educate myself on PCB design, and when the idea for this channel came to me, like, I want to make it easier for people to learn, and PCB design is one of the more complicated topics, I knew that I had to go with you as my guest. So I'm super happy to have you here. Can you remember what was your first commercial PCB design?
Oh, yeah.
You never forget your first girlfriend, right?
Yeah, the first commercial design where I worked on it on my own was for a power supply. It was a power supply for an underwater rover, basically unmanned underwater vehicle.
Okay.
And this power supply it had one job. It was basically to just power a bunch of LEDs, because these guys had this lighting system that they needed, and the vendor sells them for like a ridiculous amount of money, and they wanted to take it, miniaturize it, get about the same, lighting out of it. They didn't need this huge system. And they were hoping they could do it for, similar or less money. And so I helped them put together the power supply design and then do the layout. This is one of those projects where I don't know what happened with the design. I don't know if it scaled out. I don't know. I don't know if they actually ever manufactured one of them, to be honest. It's really interesting. One of the reasons for that is, power supply designs, I think they sound really simple, but some power supply designs can be really complex. And in this particular one, we ran into an issue where they had no choice but to get a custom transformer. And so, I helped them with the design of the transformer, got them in touch with a vendor who could supply it to them, and who could engineer it into the form factor, pretty aggressive transformer size that they needed. And at some point when you're doing this, you give them everything that they need, and you advise them of what the risks are and what to test, and you have to let it go. And hopefully they build it, and if they have a problem, they come back to you and complain, or they come back to you and say, it worked, great. Usually you don't hear from people if it works.
You only hear when it doesn't.
Yeah, exactly. They're only going to say something if it doesn't work and they have a problem. So I didn't hear anything, so I'm just going to assume that they didn't build it or it worked, and I'll call it a day.
Okay. You mentioned it was for a underwater rover, and besides like standard high-tech requirements, were there anything special about its design that was in connection with the maritime industry?
Yeah, so it's interesting because doing a power supply design like that, where you're, hundreds of watts, is already difficult, especially when you need to, do everything with discretes and a custom transformer. So that's already a difficult one. And the fact that we had to do this underwater presents a whole other set of challenges having to do with pressure-sensitive electronics. So there's this one professor, I forget his name, but he is an expert on under or high pressure electronics. So electronics that can operate at higher pressure. And so the way that they maintain the pressure in the enclosure is they actually have a transparent, I guess you'd say like a transparent plastic film, which is where light escapes from. Because remember, there's a power supply for an LED board. And then they fill that with oil. Okay. And so the water pressure pushes against that oil, and then that oil is insulating as well. So it helps with the dielectric characteristics, specifically dielectric breakdown, that modifies the allowed clearances and spacing. So if you were to boot this thing up in air, it might actually short out, and it might actually break because of ESD. Whereas if you did it in this dielectric or in oil, you may not have that problem. So that's one point. The other thing about that is that it changes the pressure environment that you're operating in. So it's not like you're filling up a capsule with air and then getting it to standard, temperature and pressure inside of that enclosure. It's actually higher pressure than it would be in air. So high pressure electronics really demands that you select appropriate packages. So this was something I didn't realize getting into the job, and I lost money on the job because I had to take extra time to go through and qualify every single IC package, every single transistor package, just to make sure it was one that was known to be, safe for operating at these elevated pressures. So most people don't operate in that environment. In fact, most electronics that are going to be in some modified pressure environment, they're going to be at lower pressure because they're probably going up in the air, or they may even be going into space. And so they're maybe at a lower pressure environment, not a higher pressure environment. So this is a little opposite of what I think most people are used to dealing with. And this was a totally new thing for me. So I had to do additional research and make sure I understand how to identify which packages are going to be most pressure sensitive, remove those from the design. And it took a lot of extra time. So it was something I was not, I will admit, I was not adequately prepared for it.
But it does sound like some fun, really.
Yeah. I mean, when you go through the experience and then you get to the end of it and, the stress is over, it's like, now it's an opportunity to reflect on what you learned and take those lessons with you. Because if you don't reflect on what you learned in any of these adventures, I guess, in designing electronics, you're doomed to repeat the mistakes. And that brings up another point just with PCB design generally. I see a lot of new people coming into the field because it is a field where demand is evergreen. There's always going to be demand for designers. Now, being that that's the case, at least here in the US and I think more in the West generally, we have a little bit of an issue with workforce, meaning that a lot of people are retiring, especially in the US. And, there's kind of this bifurcation or I guess bimodal distribution of ages. A lot of people that are older, a lot of people that are younger and just learning, and then not a lot of in between. And so a lot of what I do is to make sure that the tribal knowledge that's known by the older crowd can get transferred to the younger group that's coming in, and they can not repeat the mistakes of the past and make sure that they design things that are going to work the first time.
I see. So that's how the cooperation with Altium started for you?
Yeah, exactly. Yeah, I think, they were, obviously for them, it's marketing, right? They want to, of course, they're selling software. They want to get people out there to use the software. Totally understandable. But to do that, I think that they really felt that we provide resources for people to learn. They're just going to be better with the tool, whichever tool they use. And they're probably going to switch between tools 2 or 3 times in their career, right? You go to one company, they use Altium. You get another job in 5 years, you go to a different company, they're using pads or whatever, and then later on you come back to Altium. So that's really common. So you go between different packages. But I think for them, they thought, this is going to help us keep the product sticky, and it's going to help people learn to use the product to maximum capability. And part of that was just knowing about design and not making some of the common mistakes that you see from new people. And there's a lot of misconceptions, I think, from new people in the industry about what it takes to make an advanced design and what even qualifies as an advanced design, and what are some of the just basic, most of the time always going to work design practices that you should follow.
Yeah, I agree with that. And it's really cool about for Altium to do that, to educate. And I think a good example of that tactic paying off is the STM32 series of microcontrollers. I don't know if you recall, but when ST just dropped them on the market, they introduced super affordable dev kits, and the documentation was spectacular, and many students and hobbyists started playing with them because they were accessible. And now all those people are using them in the design because they know them as their pocket. So I think it's the way it should go. And even from my perspective, I can see a shift in electronics, that knowledge is getting more and more accessible.
Yeah, it's really important because the technology is kind of outpacing the designer's knowledge to some extent. And, the semiconductor companies have always kind of had a responsibility to teach people in some way to use the components, because otherwise you're just giving somebody a chip and they're just guessing.
Yeah.
So, the semiconductor companies have usually done a pretty good job of teaching people to use their stuff. whether it's through, like you say, really well documented dev kits or webinars. I like what Texas Instruments does. They have their like TI Precision Labs series. That's really useful, and I've actually learned a lot from them. So yeah, those resources are really important. But for a long time, PCB design was not like that at all. And the guy that really kicked it off was not myself. I'm not the first one by any means. You've had the Eric Bogatins out there for a long time, publishing in like, EDN or Eaton Times, some of those magazines. But I think the guy that really kicked it off and got the other companies to understand that this is something they have a responsibility to do for their user base and to build their next generation of customers was John Coonrod. So John Coonrod of Rogers Corporation, and if you know Rogers, you know that they make a lot of Teflon-based laminates for RF microwave. He really kind of kicked it off with his like ROG blog and some video content. I want to say in 2015-ish time frame, and that's where it really started to shift to PCBs because before that, a lot of the content that was out there was not really PCB specific. Some of it was like systems design and then programming and analysis and, some of the stuff with circuit design. And those are all important things. But, as more people started to retire, the PCB design knowledge kind of went with them. And then you didn't have enough resources for the new people coming in. And the big conferences like, PCB West, they can only do so much. They can only educate so many people at a time. And there's always something new to learn. There's always a new problem to solve. So I think folks in the industry were, really crying out for really well-detailed and application content with realistic examples. And that's the kind of stuff that we focused on at Altium. And, the other contributors like, Mark Harris, he always has great examples. Phil, who has done some stuff as well, Phil Salmini, he also has some really good examples, especially for beginners. Like, if someone's interested in like FPGA with DDR, he has a blog up right now that shows you, here's how you set this up in Vivado. That stuff can be really opaque, and there's just not a lot out there showing you how to do it. So yeah, they really like that young people are stepping up and showing the next generation that, number one, electronics can be cool. And then number two, this is how you actually jump in and get started and do it like at a professional level. So that's been the goal, and I think we've been really successful at it.
Oh yeah, Phil's the tutorial, the course he has, the paid one, it really helped me a lot with my designs. Really, I wouldn't be able to do things I did without that. So it was actually affordable. So kudos to Phil. Link in the description. Amazing tutorial. Eric Bogatin, whom you have mentioned, with Robert Feranek. Amazing videos.
I can't believe I forgot about Robert Feranek. I should have said something about it.
It's okay. I hope he won't mind.
But he won't mind. Yeah, and then there's also like Dave from EEV blog.
Oh yeah, of course.
Yeah, love the teardowns.
Yeah, they're so great. I loved watching them just for the sake of it.
Yeah, he's great. He's great to watch for sure. Yeah, and I like his methodology for the teardowns. I haven't done any teardowns myself on video. We're trying to do the other direction, which is to build it and not tear it down. But I do always enjoy watching his teardowns and kind of how he analyzes the designs for sure.
Oh yeah, that's super nice. So, as you mentioned, the getting into PCB design can be very daunting, and if you don't have any practical designs and references in some area, it's very hard to break through, especially for hobbyists. So I think we can start going into DACs now.
Sure.
And I ask about DACs specifically because I think it's a very misunderstood topic, and there are not too many references, tutorials about them. And what really stood out to me is when going through all of the data sheets that are like the first line of defense in this area, uh, they sometimes can even contradict each other from one manufacturer to the other. And there are a few topics that I really want to go through today, but I'll allow you to just deliver, because I know you're prepared for this. So please, the floor is yours.
Okay, sure. So you brought up data sheets contradicting each other. So I'd like to poke at that for just a second. So the thing about, data sheets and application notes, you have to understand the context under which they were developed. And I think sometimes people miss that. And I don't normally, like when I give a presentation, like for example, I'll be giving a presentation at PCB West this year on differential pair design. And I actually do quote an application note in that presentation. Most application notes are not worth quoting for PCB design advice because they can't be generalized to every other design. So the guidance in the note or the data sheet worked for that specific component on that specific stack up. And if it's a power system, for example, with that specific load and with those specific peripherals. So for that system, the application note is correct and the data sheet is correct.
Okay.
It's when you try and generalize it to everything else and copy those same guidelines to everything else that you then may run into a problem and create a system that doesn't work. So, where I bring up I put a data sheet or an application note in one of my presentations. I always try to say, yes, this is from a semiconductor company. Simulate this first, but here's the data that they show that this works in this particular type of instance. Should you do it all the time? Maybe not. Yeah, exactly. So take it with a grain of salt. So same thing with the data sheets, take them with a grain of salt and just be careful with some of the guidelines that you see in data sheets, specifically around PCB design. They may work great for that particular component with all of its peripherals and supporting passives or whatever else is on that little dev board. Not always. So this is something that also comes up a lot with reference designs for like power regulators, for example, and ferrite beads. They may include ferrite beads in the filter stage somewhere, and it works fine for that particular test load that they have on that power system. Or if you're like hooking it up to a DC precision load, it may work fine for that DC precision load. But if you try and take that circuit, copy and paste it to a big FPGA that's running with a bunch of digital stuff, switching all the time and pulling power very quickly through the PDN, good luck making it work. So you may not be able to get it to work because it can't respond to the power demands fast enough. So that's my little spiel about data sheets and application notes. And I think this is a really important thing about that people might need to learn, and hopefully they don't have to learn it the hard way. Excuse me. Okay, so you asked about DACs. So yeah, what do we do with DACs? How do we handle DACs? So in DACs, digital analog converter, right? It's just the inverse process of an ADC, analog to digital converter. DACs essentially just synthesize a wave or a waveform in general that you would output from or that you would convert from some sort of input bit stream, right? You're basically defining what's the signal level at each time slice, and then it kind of naturally interpolates through the output of that DAC. And then you may put it through a filter, you may put it through an amplifier or something like that to basically condition and shape the signal that you want, and then it gets delivered to a load or some other kind of system. And so DACs operate really in almost every frequency range. I mean, you have DACs that will operate very high frequencies, even used for like wireless testing. You have them built into chips as part of what the chip needs to do for waveform synthesis. Sometimes it's using, a modulation on a harmonic wave, but if you need an arbitrary waveform, you would use some kind of DAC. Or at very low frequencies with, what I think you're interested in and, what I've been interested in for a long time, which is audio. And I don't get a lot of opportunity to do audio so much, but I have done a decent amount of low-level measurement with analog. And so that's really the low frequency ADC type of application. And so the ADC layout guidelines are actually pretty similar to what you would do with a DAC, because you have two different sets of signals that you are working with, right? You've got a digital section, like for sure. You have a digital section, that's the D in DAC, okay? Then what else do you have? You probably have a low frequency analog section that you need to then output from that, right? So you've got two different types of signals, and you're going to have crosstalk. Oh, sorry, go ahead.
Yeah, I think three actually. Power. It's not a simple
power as well.
You still need to lay it out.
No one cares about.
Okay.
No, I'm joking. Yeah, that's true. You do have the power. Yeah, and then that's actually good that you bring that up, because that gets into things like references and how do we ensure that our analog terminal on our DAC is properly isolated from the digital terminal. That's a whole other can of worms. But I think what we can get into is I can actually show an example of an ADC layout. And this type of thing could actually just as easily be done for a DAC. And so the way this works is you basically have, your two sets of signals, and you kind of need to keep them separate from each other to an extent. And this is where people who do PCB design will come up with some very interesting guidelines for trying to do that. Some of them are grounded in reality and applied correctly, sometimes not applied correctly, or with a misunderstanding of what the analog signal is doing. And then sometimes they're just all over the place, and it's not going to work at all. So I've seen it run the gamut.
Oh yeah, I've seen this one.
Okay, yeah. So I'll run through this with you for viewers. So basically, here what I have in 3D. So this is an example project that we actually did on the Altium channel, and this is for ADCs. And like I said, you could do the inverse of this for DACs. Here we have two types of ADCs on here. We have an isolated ADC and then a non-isolated ADC. So I want to focus on the non-isolated ADC here, because you could just as well do this for a DAC. So we're just going to zoom in on this component, and then we'll take a look at the stack up here, and then we can kind of get some ideas for how we should lay out and route this. So first, you mentioned power, right? So over here, we have a highly integrated power supply. This is an intersil power supply, and it's actually pretty expensive, but it was a component I had a model for, and I had the circuit available, so I just kind of grabbed it and used it.
Okay.
But this particular component is space qualified, so this could be used in an aerospace application. So this entire board could just be put in as a module in an aerospace system. But you could just as easily switch out this regulator for another one that gives you the same output, and it'll work just fine. Going here into the actual chip. So this is our chip. And here what we've done is we've got an output on one side, which is our digital side. And you can see here we've got our D in, we've got our clock, and then we've got our D out nets here. And then we've got our power coming in, and then some unused pins. So this is typically what you would see if you were to look at, for example, the pinout for a DAC. The semiconductor manufacturers have done a reasonably good job of lining the pins up in these type of packages in such a way that you've got the analog interface on one side, and then you've got the digital interface on the other side. So here on the other side is where we've got the analog side, and this analog side comes out to a connector, as you can see right here on J2. And then we have a chip select, because this is a SPI bus. So we have a chip select pin right here. Typically, you would see the chip select over here on this side. It's okay if it's over here on this side, because that chip select pin, it's not like streaming data. Does that make sense? It just needs to turn on and off.
Yeah.
Yeah, so you can intentionally slow down that signal a little bit. You could do that with a series resistor or an RC filter. But in any case, it just needs to be either on or off. It doesn't switch repeatedly. So we're not so worried about this signal. What we really care about are these digital input and output signals.
It's relatively far from the analog pin. It's isolated with power supplies. So.
Yeah, exactly. So yeah, and it routes the totally other direction, right? we routed it back this way. So if you look on the back layer, you can actually see where all of those digital pins went. So it's these three, and they all come over here to this connector. Here with this one, it goes back up to the top side for this series resistor, because I wanted to keep everything on one side for this particular board.
Yeah.
But you can see here where all the stuff routed. So it's all routed away from the analog side. And then over here on the analog side, you have this pin or this line being routed completely the other direction. And then the other thing I like to point out here is where the ground is at, right? The ground is pretty much everywhere, right? Here you've got ground, right? And it's just one ground net. Here you've got ground also. And this is done to equalize the stack up, because if I have ground here, I need to have copper fill here. And then there's also stuff on the bottom, which is these digital signals, right? So these, and then we've got some other control signals coming around. And then these pins also need to have ground below them. And these pins using ground below them will ensure that they have very low noise and radiation. So these are kind of your basic getting started best practices for mixed signal systems that use a DAC or an ADC, right? It applies to both. This particular chip is an ADC, but could just as well be a DAC, right? And this is our output instead of our input. So you get the exact same type of you get the exact same type of requirements for those two systems. Excuse me. Sometimes what you have is you will have an internal reference.
Before we
having an internal. Oh yeah.
If we can touch about the grounding layers inside the PCB, because it's a 4-layer design, and while Philip Ceremony really did an amazing job about explaining why do you want 2 grounds in the middle, I thought we can touch on that, because I think it's very important especially for mixed signal circuits like this.
Yeah, sure. Now, first thing I would note is that if you route this properly, meaning like if I just as long as I don't have any digital stuff coming near this line over here, you could probably do this on 2 layers, and then it would probably be able to satisfy your noise and emissions requirements. You could probably do that. If this analog signal were really low level, and maybe it was coming out through an amplifier, or maybe you had an amplifier on the board, maybe be careful with that. One of the reasons for that is if it's really low level, it's going to have low SNR. And if the SNR is too low, then you may get some interference from any nearby digital signals coming into the analog input, and then that could create quantization errors. So then you would want to use a lower resolution on your DAC, not higher resolution. Okay. That's another misconception about both DACs and ADCs, is that higher resolution is always better. When in fact, if you have a very low level signal, you actually want lower resolution, because the natural higher distance between quantization levels in that readout or in that synthesis, it overcomes some of the noise. And that's especially true with precision measurement or precision waveform generation applications.
Oh, they're very interesting, actually. Never thought about it,
Yeah. I think that's one of those things where, you have to realize a couple of things, right? If you have an amplifier along this line and you receive noise at the input of the amplifier, you're amplifying the noise. Yeah. And then same thing here, right? If I take in a signal on this line and I receive noise on the line, I'm going to be measuring the noise.
Sure. And I can also see that it is shielded with the ground on the top layer.
Yeah, exactly. So that was the next point I was going to get into, was that, you could conceivably do this on 2 layers and it might work fine. I did it on 4 layers just because I like showing examples of 4-layer boards. I think for new people, they are hesitant to use a 4-layer board because they're going to have to pay an extra $10 or whatever per board to get it fabricated. Or they believe that, 4-layer boards are so much more expensive than 2-layer boards, which, in reality, if you're going to work professionally, you're probably going to work at minimum on 4-layer boards, not on 2-layer boards.
Oh yeah.
So that's
really not that expensive, even if you get small series from JLC or something like that. They are actually not bad. And I was really scared of 4-layer boards at the beginning, but after the course from Phil, I found 4-layer design actually to be easier than
Exactly.
2-layer.
Yeah, exactly. Yeah, especially if you do kind of what I've done here, which is signal and power, and then ground, and then signal. And you could also route power on this back layer if you wanted to.
Yeah.
Yeah. So that's kind of the vanilla 4-layer stack up. Now, I've done some power systems where it's signal, ground, power, and then signal or ground. So I've done some of those as well. Those are typically the case where you have some sort of like digital section, like maybe a microcontroller for monitoring, and that would go on the top layer. But then you have really high current. And so in those cases, you tend to need a lot of copper on the backside just in order to handle a lot of that current. So that's another kind of variation of this. But what I've shown here is really kind of the entry level stack up that works for, 80, 90% of stuff that has a digital section on it.
Understandable.
Yeah. Okay. So the other thing about the, going 2-layer versus 4-layer, you brought up the grounding, right? Doing the coplanar ground like this on the top layer, you could also do copper pour with ground on the bottom layer. Now, you could do that around all of these signals, and they would have a very clear reference around them to confine the return current around the case, around the trace, not the case. And so that would be very beneficial for suppressing emissions from around these traces. So that's another way that this could be done. But like you say, it's really easy to do it on a 4-layer board where you've just got ground on the next layer, because that ground on the very next layer is going to give you as much or better noise suppression than going with 2 layers and using copper pour everywhere.
Yeah. Especially that, as far as I remember, the basic stack-ups that you can find in PCB manufacturing available for hobbyists is usually made that the top layer and the closest one to it are very close physically. So the ground will be very, very close to the signal.
Exactly, yeah. 4 layers is where you start to get a big jump up in sorry, not 4 layers, but 4 mils on that outer thickness is where you start to get a bump up in costs, right? So that's 0.1 millimeter. So that's where you start to get a bump up in cost. But you can go with 6 mil on the outer layer. So that's it's a little thicker, but it's still going to give you really good ground noise performance, especially with like this SPI bus. These SPI buses, they're not what most people consider to be like a high speed, interface. I put that in quotations. But they can be, right? They can be because it depends what they're connected to. So the load that they're connected to actually determines how fast the signals are in these traces. So that's something else that I think people don't understand about, just a SPI bus is the amount of noise that you get also depends on the load capacitance. And in fact, the edge rates for these signals in a SPI bus, they depend on the load capacitance. So if you look on a data sheet, you'll see a rise time specification for that bus, and it will be given as a function of a test load capacitance, typically, on the order of picofarads. And so as that load capacitance gets smaller, meaning more advanced chips, then these signals will get faster.
Yeah, that's something to consider. And I think it's a good moment to ask a question. I have seen in many PCB designs for audiophile DACs, or not audiophile DACs, whatever, but for audio DACs, that people tend to provide isolation for the control signals.
Yeah, exactly. So that's another great reason to kind of show some of this and show what isolation really looks like. Because I think what people will do, especially if they're newer, is they'll say, well, I want to prevent, this signal from interfering with these signals over here. So I'm just going to make a big cut right here in my ground, and then we're done, right? And this is, it gets even worse, because if you start looking at data sheets for some of these components, if you look at the data sheets, some of the pins will actually be named analog ground and digital ground.
Yes.
And so it almost implies that you have two separate pieces of copper, which is actually not true. You're not supposed to do that. If you actually look at some application circuits in those very same data sheets, they will show that those two pins are connected together, and they're supposed to be connected together. And you do that through, well, what we're showing here, right? Through a bunch of copper.
Yeah. I've seen even data sheets from older chips, actually, but from like 20 years ago, 15 years ago, that will recommend splitting grounds and connecting them just under the chip.
That's true. Yeah, they will sometimes do that, and the reason they're doing that is because they're saying, well, just connect them under the chip because you need to have those pins connected in order to ensure that you're reading a consistent voltage reference on both sides of the chip. But they're doing that because they want to try and give you a simple way to confine return current from a low frequency analog signal. And they're trying to help you in a simple way prevent interference from this digital section. The problem with those types of guidelines is that if I put a big split right here and then I route a signal from the right side of the screen where my mouse is over to the left side of the screen on the top layer, now I've routed over a big split in the ground plane. And so now I'm going to get a bunch of radiated emissions.
Yeah. You have basically cut the return current, right?
Exactly, yeah. So for whatever trace I'm trying to route between those two regions, yes, I would get a big discontinuity in the return current. Exactly. And if it's an impedance-controlled signal, like a single-ended impedance-controlled signal trying to route across that plane, now there's a chance that depending on how big that gap is and how fast the signal is, that interface wouldn't even work.
Yeah.
Now, if it's differential, there's a possibility it still can work, but you have to design the differential pairs properly. And most people don't do that. They just take the design as it was intended over the ground region and then route it across. And then they get to the other ground region, and it's in that middle area where you have the split, where you have the big discontinuity that then creates the potential for the interface to not work. So speaking of isolation, there are isolated components, and the way you properly do isolation is basically like this, right? You have all this stuff over here, and it doesn't cross onto the other side. You have all this stuff over here, and it doesn't cross over to this side, and that's true isolation.
Okay.
What sometimes people will do is they will look at this other component that we have here, okay? And they'll say, oh, okay, I have a 5-volt input here and I have a 5-volt input here. So I'm just going to route my power across here. And then you have a big area here where you could receive noise on your power rail. And if it's really extreme noise, then you could actually interfere with the measurement over on this other side or with the waveform generation over on the isolated side. And especially if you're trying to, if this is a measurement application and you're measuring a low-level signal, that low-level noise is problematic because it could actually be comparable to whatever the signal is that you're actually measuring. And so now you've totally distorted that signal.
Yeah.
Yeah, exactly. So the other thing that they might do is they might say, oh, okay, well, I isolated this component, but I can still route stuff across this gap. Well, now you don't have isolation anymore. And that's especially important in something like high voltage, where you are doing this for galvanic isolation. And that's a safety thing. That's not just a noise thing. It's a safety thing. And so if I route some traces across this isolation gap, and let's say those traces go to a connector, well, now I don't have actual galvanic isolation anymore. So now there's a safety problem.
Yeah, it's just
yeah, or there could be an EMC failure due to conducted emissions.
Okay. Before that, you were talking about references. I think it's a really good topic, actually, if we can go back to it.
Yeah. So references, so ADC references. So all ADCs and DACs have some sort of reference that they use to define signal levels, whether it's synthesis or measurement, right? And for ADCs, this is really important that you have a very low noise, very stable reference. The reference can have a little bit of noise, but as long as the noise is very low compared to whatever it is you're trying to measure, then there really won't be a lot of error between the measured signal and the actual signal. Sometimes with those references, you can do what I've done here, which is you have, a power pin on one side that's supplying your IOs, and then you have another pin on the other side that supplies your analog supply. And this particular component has a built-in reference. So some references are external. They're actually an external component. And that's when you really need high precision as well as good temperature stability. So precision measurements can be distorted when the system heats up as it operates. And the voltage that a reference circuit will output depends on that temperature. So you want really low temperature drift. So there are precision voltage references that you can use for these kinds of applications. And they're really simple. They're just a voltage source. So they're not very complicated to wire up into a circuit or to place or use, right? You just wire up the output voltage, put some capacitors to provide filtering, target that capacitance such that it's, maybe 10 microfarads. Usually there's an application circuit in the data sheet. You can usually just follow that guidance. They aren't meant to source power or, any appreciable levels of current. They're just a stable reference. They're basically hooking up to a high impedance input. So you just want that voltage to be stable. So like, for example, if I had a reference voltage I needed to use in this kind of system, I wouldn't want to put it like here on the back layer right next to all of these digital things, right? And then route like a trace from the reference over to my DAC or my ADC or whatever, or even if it's like an amplifier, you're using it with a reference. So why wouldn't I want to do that?
Because it will couple noise.
Yeah, exactly. So it could receive noise from one of these other signals, and that noise could be low, right? Especially if we have ground very close on the next layer. But say we didn't have this ground, or we had a thicker outer layer, right? And I just routed a long trace next to these digital traces. Then what's going to happen to that rail, to that trace for that reference voltage? I'm sorry?
It's going to get contaminated.
Yeah, it's gonna have even more noise. Yeah, exactly.
It's kind of like taking a bath and dressing up in dirty clothes.
Yeah, exactly. So yeah, it's a good idea to place those references close to these chips. Or if you do have to route them, you isolate them in some way. So meaning they are routed on their own layer, far away from anything else. They're routed with larger traces or reasonably sized rails. So that way they have really low inductance and they can receive less noise. So some really simple guidelines for using those that will help ensure you have low noise. And then the other thing beyond references that might be needed in these systems is really this line right here. Depending on the frequency of the signal that's going out on this line, you could really have return current kind of existing everywhere in this copper. So, if you're at the kilohertz level, like high kilohertz, meaning, at the upper end of the audio range, that's really where you start to see the return current get strongly confined around this trace. But let's say you're in the hundreds of hertz range. Where's that return current?
Everywhere.
Everywhere. Yeah, it's everywhere in this copper. Yeah. It's everywhere in this piece of copper and in this piece of copper. Yeah, it's everywhere. So for that reason, sometimes what you'll see is you'll actually see those signals routed differentially. And so with differential routing, if you have, like, for example, a differential amplifier operating at low frequencies, that differential pair, it forces or defines the return current to be in the neighboring trace. So that's where your return current exists.
Yeah. Yeah, that makes sense. Yeah.
Yeah, exactly. Now, if you put some ground nearby, there will also be return current in the nearby ground. So that's one of the misconceptions I think about differential pairs, is that just because I route the two pairs next to each other doesn't mean that there's only return current in the complementary pairs. If I put some copper nearby, there's also return current in the copper.
Never thought about it. I actually thought that when I use a differential pair, the return current will be confined in that. So yeah, that's something I never considered.
Yeah, exactly. So in that case, with like audio, let's say it's a low frequency audio signal coming out of a differential amplifier routed over differential pairs, then you would want to pull back the copper for around those pairs. And you could even now remove some of the ground below that differential pair. And like I said, the reason to do that is to really confine the return current, because with that differential pair, you can route differential pairs without very close ground, and they will maintain tight return current, and they'll have lower emissions than you would if you were to, let's just say, route a single-ended signal without ground. So that's possible. And think about what happens when you routed a differential pair over a cable, right? When you take a differential pair, you route it over a cable. It's not like you have uniform ground everywhere around that cable. I mean, there are shielded cables, but that's not always the case. And those interconnects still work. So you can route differential pairs like that as long as they're tightly coupled to each other.
You mean like physically close on the PCB, right?
Yeah, like physically close to each other. Yeah.
Same plane, very close spacing, right?
Yeah. So that very close spacing is important for analog, for the reason that I mentioned. And this is now where you start to see a misconception when you get to really high-speed digital, right? When you get to really high-speed digital, like with computing interfaces, people will say, oh, well, with low-frequency analog, I can do these things where I just route the pairs close together and then they always work. And then maybe I put some ground nearby, but it doesn't really affect the noise as long as that ground is just disconnected copper or an island or something. You see that kind of thing. And that's actually not the right way to do it with a high-speed differential pair. Because with a high-speed differential pair, you have an impedance specification and a loss specification you're trying to hit. Whereas here, we're just trying to make sure that we know where the return current is.
Yeah.
So we have different goals we're hitting in those designs.
Yeah, it's all between low level.
I mean, with audio, it's important to maintain an accurate accounting of where your return current is going to be. And one way to do that is to use components that have differential interfaces.
Yeah, that's actually quite interesting, the difference between low speed signals that the return current can just go anywhere because it will look for the lowest resistance on the PCB, and the high speed where it's the opposite. The return current will try to be as close to the original signal as possible.
Yeah, exactly. And that's because that's the path of lowest reactance.
Yeah. But two more things, if we may. The time is running out, but I hope we can touch on them.
Sure.
So you mentioned high-speed digital signals, and lately with high-resolution files, with high-resolution music and streaming, it's getting really, really popular. The digital signals that are going into the DACs, they are going in 20s, 50 megahertz range. Would you say that we should treat them as high-frequency lines, and how should we design them?
This is a great question, because this is where someone will I think bring up the difference that, well, what they'll do is they'll look at the signaling rate, which is, like that 50 megahertz, right? That's your clock speed, essentially, right? It's a bit rate. The bit rate is not what makes something high speed, right? It's the edge rate of the digital signal in that bit stream that makes it high speed. So you can have a 20 megahertz signal, which, I mean, it is, barely scratching the surface of the RF world, but it could contain a high-speed digital signal, and it could emit noise into the RF range if it's not routed correctly. So that's another misconception, is that, the clock frequency is what determines when something is high speed. And this is something I see all the time from newer designers. It doesn't matter if they're doing audio, if they're doing digital, whatever. They seem to think that the clock speed is what makes something high speed. And that's not correct.
Okay, so how should we approach this topic?
Yeah, so it really depends on the interface that is being used to generate those digital signals. And really, the best thing that you can do to always be safe when you're routing a digital bit stream into any component, doesn't matter if it's a DAC or if it's something else, is to do it like I've done here with this SPI interface, right? We have the SPI interface routed over ground, right, on the next layer. And then if we just look at the layer stack here, we can actually see what the thickness is for that layer. I seem to recall in this particular project, it wasn't too thick. Yeah, only 5 mils, right? So it's a pretty thin layer. So yeah, this routing directly over ground for these digital signals, that's your best bet for doing it correctly. And that's one of the reasons why I say that, this kind of 4-layer board is really your entry level stack up for someone who wants to do anything with digital signals.
Okay, and what about signal integrity of this signal? Should we be aiming, because I2S, the standard for the audio interface between chips, is I didn't see that it had defined impedance. So should we be just using some kind of rule of thumb about the width of the traces?
Yeah, this is a great question. So you're right. These slower speed, parallelized buses that are either push-pull or open drain functionality, so like, I2C, I2S, SPI, they don't have an impedance specification, meaning you are not required to use a 50 ohm trace right here. So if you look at the width here, right, the width is 10 mils, and then the layer thickness is 5 mils with a decay of 4.1. So if I just go to the impedance tool real quick, we can get a quick calculation of the impedance, right? You can see here that I'm going to be a little bit under 50 ohms for that 10 mil trace, right? If I just set this to, say, 10, you can see here that my impedance is 46.73, right? Okay, so you don't have to have a 46 ohm trace here, right? I could make this 12, I could make it 15, I could make it 5 mils, whatever is easiest for me for routing. The issue is that eventually what happens is that if this trace gets long enough, then the driver that is connected to this particular connector and that receiving component, right? Because this is my output trace, and then here's my input. Whatever is connected to this component on the other end, it is now going to see that impedance discontinuity. So this is where everyone brings up the critical length rule. And, critical length rule is appropriate for analyzing when you need to impedance match this type of signal. The problem with it is that everybody starts using it as an excuse to not impedance match something like DDR, which you absolutely must impedance match. Or they try to use it as an excuse to not impedance match Ethernet or something, right? Which you absolutely must impedance match. So it's an appropriate rule for figuring out when you should start to add in this series resistor right here, because this series resistor, which is only 22 ohms, is going to approximately match whatever the driver output impedance is that's connected to this connector to about this 46 ohms that we have here on this trace. Because when SPI buses get long enough, the bus may not work anymore. And it's because you don't have this series termination on that trace. So SPI bus buffers, their output impedance could be, the 20 to 30 ohm range. It really depends on the voltage level and the current that they're sourcing. It varies, but it tends to be in the 20 to 30 ohm range. And so by adding in this 22 ohm resistor here, for most SPI bus drivers, that's going to set the input impedance looking into this trace to be about 50 ohms. Okay. That makes sense?
Yeah, absolutely. absolutely.
Yeah. So that's one of the big signal integrity points. And then the other reason that we like to do this coming off this connector is because it slows down the edge rate a little bit, which is kind of interesting, right?
Oh yeah.
The reason you need this is, oh, sorry, go ahead.
No, I really wanted to ask about slowing down because that's something that Phil Selmany also mentioned.
Yeah, exactly. So this series, it's kind of interesting, right? Because, the reason that you need the impedance consideration and this resistor is because the bus is fast, right? So you add the resistor so that the impedances are matched, but that slows down the signal. So now the signal doesn't need the impedance match. It's a bit contradictory and circular if you think about it. But one of the reasons that you add this is more for EMI, which of course is related to signal integrity. It slows down that edge rate a little bit, so that way you get less radiation coming off of the transition through this connector. You'll notice I've done something else here with this connector. So what do you notice about the pins?
Oh, I can see that every signal has its own ground.
Yeah, exactly. So I've interleaved the ground through these pins. Now, obviously you can't do that on every connector, but because I had full control over this layout, I was able to do that. So I've interleaved the ground like this because that's also going to help suppress radiation from any signal that's transiting over this pin and whatever cable is connected to it.
Yeah, and I can also see that every time you switch layers with high-speed signals, you also place a via very close to it.
Good point. Yeah, I wasn't even going to bring that up, but yes, you can see it's right here. Yeah. So the reason I've done that is because as you transit across, all the way across the stack up, you maintain a ground reference near this signal pin. And that also helps prevent radiation into the inner layers of the stack up. And in fact, something as simple as this, I have actually seen on client boards, this kind of thing cause EMC failures repeatedly. And so then they come to me and they say, we're having this EMC failure. We think this is what we need. Usually they want to do like 10 other things at once. So you end up doing a lot of changes on the boards in those cases. But yes, you brought up exactly the right point. Yeah, you keep that ground here for that signal transition.
Okay, yeah, that's really good. And the last thing, I think it's one of the most important, and I think it's one of that is getting overlooked the most, is decoupling.
Mm-hmm.
If we can, if we can talk about
placement of capacitors. Yeah. So if you look around here, in fact, I put it in 3D, you can kind of see what's going on here, right? So we've got two big capacitors here for this power supply. Okay. But if you start looking around near these power pins, right, we've got a capacitor, and here we've got a capacitor. Now, this capacitor is not running at super high speed. It doesn't need, super fast bursts of current, and it's not like an FPGA where you could have 1,000 IOs, literally 1,000 IOs switching all at the same time, right? Yeah. There are there's like four IOs that you have to worry about on this, So we're way off from what you would need to do in a really high-speed digital system. So in those high-speed digital systems that where the main processor is on a BGA, you could have, hundreds of these capacitors mounted on the back side of the board, directly onto the back of the BGA. So here, I've placed these decaps close to this power pin for a pretty simple reason, right? Whenever this supply needs to draw power through this rail, it's actually drawing power from these capacitors. Okay, so these capacitors are really what are responsible for providing power, and then they periodically recharge and then discharge as this signal needs to get power. So what you want to do is ensure that you have really minimal response time. They can respond as fast as possible. And they do that by having minimal resistance and minimal inductance along this path going into this pin. And then you can see the same thing over here on this power pin for the digital supply. For the digital supply, you see we've got a cap here, and I've got a cap here, and they're right next to the pin. And in fact, I put them right next to the ground too. I've seen a lot of debate as far as to like, should you put this on the back side? Should you put it on the top side? I don't really get into those debates simply because you're really trying to optimize, closeness to the pin, as well as like, can we put them on the back layer at all? Is there room? Are we just trying to do one-sided assembly so that we can reduce the assembly cost? Things like that. The point is, generally, just as a general rule of thumb, as long as you get them as close as possible to these pins, then that's the right thing to do. So same thing here. We try and get minimal inductance along this path without getting so close to these other signals that we might have some clearance issues. The clearance thing is part of DFM, right? So I could take this trace, right? You see it's 13 mils right here. I could double it to 26 mils, right? But now I'm violating clearances over to these other signals, and I'm even violating clearances over to this other pin. And so the clearance issue is important because your fabrication house is only going to be able to fabricate down to a certain level of precision. And so they're going to have some minimum clearance that you need to hit. And if you violate that, your costs either go up or you just won't be able to manufacture it. They won't bid it at all.
Yeah, you always have to check with the specs that they have on their website. What they can
exactly.
do.
Exactly.
Just set the design rules when I starting a layout.
Yeah, exactly. So you can see here, in Altium, it flashes green like this. Other CAD systems, they have their own, violation indicator that they use when you do this kind of thing. So it's very clear when you've made a mistake. So yeah, you set those clearances first, and then you let the tool tell you when you've broken.
And even when you export, I use KiCad. Even when you export to the PCBs, you do the electrical rule checkup, and it will flash all the errors, and they're usually quite some. So it's really hard when you set up your workspace properly. It's hard to go wrong, really.
That's true, but don't be surprised when you've got 50 silk screen errors at the end of your design.
Absolutely. About the decoupling capacitors, is there any rule of thumb for selecting their values? We should go with 100 nano and 10 micro, or is there any other suggestion from you?
Yeah, that's another really good question. So there is this rule of thumb that Eric Bogatin actually did a really good job of looking into and trying to find the origins of it. And that is the kind of what you mentioned, right? The 100 nanofarad or 10 nanofarad, 1 microfarad, and then 10 or 100 microfarad capacitor values all in a line. And I've kind of done that here, right? This is 0.1 micro, and then this is 1 micro. These were based on an application circuit for this particular component. And of course, if we, for whatever reason, found that we were getting, too much switching noise on this D out rail, so like a measurement right here on this pad, then these are surface mounts, so I could just solder another cap right on top of this to try and get the capacitance to come down and see if that helps. So that's one way you can kind of evaluate whether or not you have enough capacitance. The other reason that they've done that is because they're trying to extend a low impedance bandwidth for this rail out to as high of a frequency as possible. So that way, this rail can provide power to these IOs at such that it supports their very fast switching speed. So just kind of as a rule of thumb, that's why that guideline exists. And so you can really clearly see I've done that here.
Yeah.
Now, the other reason that I have this big rail like this is because if you look on the next layer, right, I have ground down here. All of this rail has capacitance to ground.
Yeah.
So even the physical structure of this big rail acts like a big capacitor that also supplies power out to high frequencies. So there are tools that vendors provide, like semiconductor vendors provide, that will actually help you size and count the number of capacitors of different sizes that you need in order to support their particular components. So check out those guidelines and follow those, and they will help you at least determine the total amount of capacitance you need. It's then your job as the designer to pick out the parts that are going to give you that amount of capacitance in different case sizes. And then you have to lay them out and arrange them correctly in the layout so that they actually work the way that they're intended to work. So it's not just a simple matter of like looking in the data sheet and they say, oh, I need, 5 10 microfarad capacitors or 10 nanofarad capacitors, whatever. It's not exactly that simple. It's really a matter of, placement, routing. Do I give enough plane capacitance like you can see here? Do I have low enough inductance between these capacitors and along this loop? Have I minimized via transitions where possible? You can see here I only have ground via transitions, which is fine. So those are the kinds of things you have to think about when you're selecting those capacitors.
Okay.
And actually, this brings up a good point. I actually I have it on my list. I need to do a video on sizing with bypass and decoupling capacitors because it's a little bit of a complex topic. But there are some simple rules that you can follow that tell you the total amount of capacitance up to some bandwidth limit.
Yeah, if you do, we will link it in the description.
Okay.
So people can find it easily.
Countdown's on. Now I guess I got to do it, don't I?
Yeah. Sorry for that. Kind of kicked you into it.
That's okay. If you ever want to get me to do something, I guess you just got to ask me to do it on camera. So
I'll remember that.
Yeah.
Okay.
Yeah. You remember that for next time.
I hope there will be one. This was
Yeah, definitely.
I really enjoyed this session, and I'm super happy that we actually touched on very basic stuff, but we also went to more expert level topics, and I'm super grateful for your involvement in this first episode of podcast. So you kind of did it blindly, very brave.
Yeah.
Maybe not very smart. We'll see.
I think I'd like to leave listeners with one takeaway, which is, I've discussed a lot of stuff just in this short time. One challenge that you have to get good at as a designer is bookkeeping. What I mean by that is keeping track of all the stuff, all the points in that checklist. That's the challenge, and that's what takes practice. And so if you can get good at that, you've got a much higher chance of being successful.
Yeah, that's amazing point. That's something that I learned the hard way. And when I usually finish sketching my design, especially in the first stage when you have just this spaghetti of rat's nest on the PCB layout, then you like didn't I do like a big mistakes? So didn't I mix the digital with analog? Do I have the decoupling? Do I have the right sizing for parts, for traces? Yeah, it really changes a lot. It really reduces the amount of dots that you get.
Yeah, for sure.
Okay, so thank you very much for coming. It was
Thank you.
Fantastic experience. I learned a lot today, and I hope our viewers did too. Check out the links to Zachariah website, to Altium guides, to everything that is connected to him. And I'll see you in the next one. Thank you.
Thank you.